Good morning, students. Happy New Year to all. Today we are starting with a new chapter, coordination compounds. Coordination compounds are very important. Okay, they are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Okay, now let us see what is meant by coordination compounds. Coordination compounds are formed from transition metals. Okay, transition metals formed a large number of complex compounds in which metal atoms are bound to a number of anions or neutral molecules. Okay, so transition metals formed a number of complex substances, complex compounds, okay? Complex compounds in which the metal atoms, are bound to anions or molecules. Okay, such compounds are called as coordination compounds. Okay, example, chlorophyll is a coordination compound in which magnesium is the metal present. Next, another example is hemoglobin. Hemoglobin in which iron is the metal. Another example is vitamin B12. Vitamin B12, here cobalt is the metal present. Okay. Also, coordination compounds are wide applications. Okay. They are used in electroplating, then textile dyeing, medicinal chemistry, etc. Okay. Textile industry. Medicinal industry, etc. Detailed study we will do later. Okay. Now, let us discuss more about coordination compounds. First, definition of some important terms pertaining to coordination compounds. So, different terms present in coordination compounds we are discussing next. Okay. First, addition compound. What is meant by addition compound? Addition compound. So, compounds made up of two or more stable compounds by crystallization in a fixed stoichiometric ratio are addition compounds. Okay. In addition, compounds are made up of two or more stable compounds. Okay. By crystallization. Okay. They combine together and form compounds, addition compounds in a fixed stoichiometric ratio. In a fixed stoichiometric ratio. Okay. These are called as addition compounds. Let us take few examples. KCl, it's a stable compound. Then MgCl2, then 6H2O. All these stable compounds combine together and form a compound called carnallite. KCl, MgCl2, 6H2. They combine together and form carnallite. This is an addition compound. Okay. Now, take another example, CuSO4. Copper sulfate, 4NH3, 4 molecules of ammonia and water form a compound CuSO4 NH3 4 times, 4NH3. Then H2O. What is this compound? It is tetramine copper 2 sulfate monohydrate. Okay. Tetramine copper 2 sulfate monohydrate. Okay. Another example. Okay. Now, what happens when they form a solutions? That is, according to that, the addition compounds are divided into two. Okay. First point, those compounds lost their identity in solution. These are called as double salts. First type of compounds, they lost their identity in solution. They are double salts. Let us take an example, more salt. More salt is an example. FeSO4, more salt is FeSO4, NH4 twice, NH4 twice SO4, 6H2O. Okay. In solution, what happens? They completely ionize and they lost their identity. Fe2 plus, then 2NH4 plus, then SO4 2 minus, SO4 2 minus, then 6H2O, they ionizes like this. So what happens? They lost their identity. Next is more salt. Another category, second type of addition compounds, what happens? Those retain their identity in solution. These are called as coordination compounds or complex compounds. Compounds retain their identity in solution. Okay? They retain their identity in solution. Let us take an example. FeCN. FeCN twice. Reaction with 2KCN. What happens? 4KCN. Okay. They converted to FeCN 6 times, K4 FeCN 6 times. This is an example for coordination compounds. This compound is called as potassium ferrocyanide. Potassium ferrocyanide. We are studying about these compounds in this chapter. Now, next point is coordination entity. What is meant by coordination entity or coordination sphere? Coordination entity or coordination sphere. What is meant by this? So, it constitutes a central metal atom or ion bounded to a fixed number of ions or molecules with coordination bonds. Okay. So, through coordination bonds, what happens? It constitute a central metal atom or ion. Okay. Central metal atom or ion bounded to a fixed number of ions or molecules. Okay. Ions or molecules through coordinate bonds. Through coordinate bonds. Okay. Take one example. COCl3 NH3 thrice. this case, here CO3 plus is the metal atom. Metal atom. Okay, the ions attached to this metal atom. Metal atom through coordinate bonds they attached to 3 chloride ions and 3 ammonia molecules. 3 ammonia molecules. So this sphere is called as coordination sphere or coordination entity. There are lots of other examples. NiCO4 times, then PtCl2 NH3 twice, then FeCN6 times, etc. are examples. Okay. Now, third point is central atom or ion. We already discussed central atom or ion. In a coordination entity, atom or ion to which ions or groups are attached at a definite geometrical arrangement around it is called as central atom or ion. Okay. In a coordination entity, atom or ion. Coordination entity, atom or ion to which a fixed group of ions or groups are attached. Ions or groups are attached through coordinate bond. Okay, in a definite geometrical arrangement. In a definite geometrical arrangement. So, metal atoms are the central atom. Those atoms are the central atom. Okay. Example we can take K2 PtCl6. Example K2 PtCl6. Okay. So, here the central metal atom is platinum. Platinum 4 plus is the central metal atom, and this metal atom accepts lone pairs from the ligand. Ligand is Cl. Okay. This accepts lone pairs from ligands. That is the groups which are attached to this central metal atom. So these are also called as these atoms. These central metal atoms are acts as Lewis acids. Okay. Lewis acids. So they act as Lewis acids. There are lots of examples. FeCN6 times 3 minus. Here Fe3 plus is the central metal atom. Okay. There are lots of other examples. Now next, fourth point is ligand. Fourth point, ligand. What is a ligand? Ligands, donor atoms, molecules or anions. They may be molecules or anions which donate a pair of electrons to the central atom are called as ligands. They are donor atoms. Okay. Then anions or molecules. Okay. Which donate a pair of electrons to the central atom, to the central metal atom or ion. Okay. These are called as ligands. These ligands they are electron donors. So they are called as Lewis bases. They are Lewis bases. Take few examples. Ni, NH3 6 times. Here Cl2. Ammonia is the ligand. Okay. Like this, there are lots of examples. Next point, coordination number. What is meant by coordination number? What is meant by coordination number? It's defined as the number of coordinate bonds. So we know the metal atom is attached to the ligand through coordinate bonds. So this coordinate number is defined as the number of coordinate bonds formed with central atom by the ligands. Number of coordinate bonds formed, number of coordinate bonds formed with central atom or ion by ligands. Okay? By ligands. Let's take few examples. AgCN 6 times. 6 times twice. AgCN twice minus. Here, what will be the coordination number? 2 ligands are attached. So, coordination number is 2. Then, Cu NH3 4 times 2 plus. Coordination number is 4. Another example. FeC2O4. This is oxalate ion. C2O4 is oxalate. 3 minus. Here the coordination number is 6 because this oxalate is a bidentate. They are attached to the metal atom through two coordinate bonds. So they are called as bidentate. So coordination number will be 6. 3 into 2, 6. Next, CO, En thrice. En thrice 3 plus. Okay, here the coordination number is 6. Here also this is ethylene diamine. Ethylene diamine is a bidentate. So its coordination number is 6. Next, counter ions. What is mean by counter ions? Counter ions. Ions outside the square brackets are called as counter ions. Ions outside the square bracket are called as counter ions. Okay. Take an example. K4 FeCN 6 times. K4 FeCN 6 times. Which one is the counter ion? Here K plus is the counter ion. Okay. Next, we are discussing coordination polyhedron. 6th point, coordination polyhedron. So, 6th point, coordination polyhedron. Okay. So, spatial arrangement of ligands around the central atom or ion is called coordination polyhedron. Okay. Spatial arrangement of ligands. Spatial arrangement of ligands around central atom. Or ion is called as coordination polyhedron. Okay. There are different types of spatial arrangement. First one is octahedral. Like this. 1, 2, 3, 4, 5, 6. 6 ligands are attached spatially around a metal atom. L represents the unidentate ligand. Okay. Unidentate ligand. And M is the metal. Okay. Now, second one, example is CONH3 6 times, 6 ligands are attached. Next, tetrahedral. This arrangement, and it is, example is nickel CO 4 times, nickel carbonyl compound. Okay, carbonyl compound is the ligand and nickel is the metal atom. Now, the third one is square compound, square polyhedron, PtCl4 2 minus is an example. Next, fourth one, trigonal bipyramidal, and fifth one is square pyramidal. So, like this, different types of arrangement are possible. Now, seventh one, next point is oxidation number. Seventh point is oxidation number. What is oxidation number? Oxidation number of central atom in a complex is the charge present on this metal atom. If all the ligands around this central atom along with their electron pairs are removed, they show a charge. This charge is called as the oxidation number of the central atom. Okay, oxidation number of the central atom in a complex is the charge present in the atom, that is in the metal atom, or present on it if all the ligands along with their lone pairs are removed from the central atom. Okay. Let us take an example, and this number, this oxidation number is represented as Roman letter in a bracket. Okay. Example, CONH3 6 times 3 plus. Here, cobalt is the central atom and its oxidation number is 3. Like this we are writing. Then, FeCN 6 times 4 minus. Here, iron is having the charge 2, oxidation number 2. Okay, like this. Now, next point is homoleptic and heteroleptic complexes. Homoleptic and heteroleptic complexes. Okay. Now, complexes which have only one type of ligands are called homoleptic, and complexes which contain more than one type of ligands are called as heteroleptic. Okay. Compounds containing only one type of ligands. Examples, these ligands, CONH3 6 times, 3 plus, CONH3 6 times 3 plus, it contains only one ligand NH3. Next, compounds containing more than one type of ligand. Examples, CONH3 4 times Cl2. This is the coordination sphere. So, Cl2, it contains two types, ammonia and chlorine. Two types of ligands are present. Such compounds are called as heteroleptic complexes. Now, let us write in common. That is, if we take an example, NH3 6 times, then Cl3. If we take this example, then here the central atom is CO, central atom. Okay. Now, this is the ligand. Okay. Now, outside the bracket is counter ion. Okay, and coordination number is 6. 6 is the coordination number. Okay, what about coordination sphere? Those inside the square bracket are coordination sphere. This is coordination sphere or coordination entity. Okay, this much about the coordination compounds. Okay. Next is HSAB principle. HSAB principle. That is hard and soft acid and base. Okay. Hard and soft acid and base. HSAB principle. A particular metal ion is having a special tendency to form complex with particular ligand. Okay, metal atom has a tendency to form complex with a ligand. Okay, here metal atom is a Lewis acid and ligand is a Lewis base. So, metals are classified into two types, soft acid and hard acid. Ligands are classified into soft base and hard base. Okay, like this. Now, while forming a complex compound, soft metal prefer soft base, okay, and hard metal prefer hard base. Okay, soft metal, soft base, hard metal, hard base, like this. Okay. Now, let us categorize them: hard acid, soft acid, then hard base, soft base, like this. Now, hard acids are Li, Be, Sc, then manganese, iron, okay, cobalt. These are hard acid, iron and cobalt. These are hard acids. Okay. Now, soft acids, platinum, +2 and +4, then Cu plus, Ag plus, Au plus, calcium. These are soft acids. Okay. Then hard base NH3, RNH2, H2O, OH minus, O2 minus. These are hard base. Soft base H minus, R minus, C2H4, R2S, then carbonyl Cn minus, etc. are soft bases. So, hard acids normally form compounds with hard bases and soft acids with soft bases. Okay, like this. This much about coordination compounds.